In this video, we're going to continue and complete our discussion of how we solve linear constant coefficient differential equations in order to perform system analysis in the time domain. Previously, we looked at how do we solve general case equations by first solving the single input case and then generalizing them to find the zero input response and the zero state response of a general case differential equation. Those methods provide a complete solution for us, but there are a few special cases that we need to handle, and so that's what we'll be talking about today. And then, after we go through those special cases and provide examples of each one, we'll return to the topic of system classifications. We'll return to the ideas of system stability and complete our methods for determining whether a system is stable or unstable simply by looking at the differential equation. So far, we only have a simple model for stability based on bounded input, bounded output stability. Now we'd like to extend that to being able to classify a system as stable or unstable based just on the coefficients in the differential equation. In our solution of linear differential equations, there are two special cases that we sometimes have to deal with. The first special case is when the input signal, x of t, what we're calling the forcing function, has the same functional form as one of the terms in the natural response of the system. For example, if we have a system with a natural response that has the form k1 e to the minus 3t plus perhaps some other terms, and I'm exciting it with an input that also has an exponential e to the minus 3t term. If this were the case, then this would be a combination that would fall into this first special case. Typically, when we look for the form of the forced response, we use this table to look up the forcing function, the input signal, and associated forced response. Now in this table, there's a few entries that have little asterisks, a little bit of fine print for us. Those cases say that for entries in the table that include exponentials, e to the at forcing functions, that would be e to the at by itself, e to the at times a cosine, or e to the at times some power of t. If that exponent is also a root of the characteristic equation, perhaps repeated a few times even, then the forced response has to be modified from what it says in the table. They would have to be multiplied by some t raised to the power of r, where r is the number of times that the natural response root appears as a root of the characteristic equation. Now that's a lot of words, so probably better to work with an example. Here's a differential equation that we haven't solved yet. Y double prime of t plus 3y prime of t plus 2y of t equals x of t. This is a single input case differential equation because we just have x of t on the right side, so this will keep it simple for us. If we were going to solve this differential equation for a particular input, x of t equals 2 e to the minus 3t u of t, and we want to find the forced response of the system for time t greater than 0. In this case, we don't need the initial conditions of the system if we're just finding the forced response. Now, before we dive into finding the forced response, based on this special case, we should get in the habit of checking the form of the natural response. This particular differential equation has a characteristic equation of s squared plus 3s plus 2, and we set that equal to 0 to find its roots, and find that s equals either minus 1 or minus 2. So we have two real roots, which means the natural response will have the form of some k e to the minus 1t and another k e to the minus 2t, using those two roots of the characteristic equation. Now in this case, our forcing function is not the same as any of the terms of the natural response, and so this one does not fall in our special case. But we'll run through the solution of this so that we can compare it to the case where we do invoke the special case conditions. In this particular case, x of t is e to the minus 3t, so the forced response is an exponential times some unknown multiplier c. If we plug the forced response into the original differential equation and equate it to the actual input, we would see that the second derivative of our assumed forced response is 9c e to the minus 3t. The first derivative is minus 3c e to the minus 3t multiplied by the 3 coefficient from the differential equation, plus 2c e to the minus 3t for the linear term, and set that equal to the actual input, 2e to the minus 3t. Solving this equation, we see that 2c equals 2, c must be 1, so our forced response is 1 times e to the minus 3t u of t. Same form as the forcing function with a different coefficient out in front. Now, what if we solve that same problem with some set initial conditions and wanted to find the forced response where the input signal happened to be a 2e to the minus 1t u of t. Now this is a case where we are now working with that first special case condition. Our forcing function, our input signal, e to the minus 2t, has the same form as one of the terms in the natural response, which in this case, if we had solved the zero input response for these particular initial conditions, we would have seen that the zero input response is 5e to the minus t minus 3e to the minus 2t u of t, and we'll leave that to you to prove. But in this case, again, we have a natural response term that matches our forcing function, so we're in our special case. Now, if we didn't notice that, if we just plowed ahead with our normal method of solving the differential equation, let's see what would have happened. So if we didn't notice that the natural response had a term that had the same form as the input signal, we would have said, well, our 2e to the minus 1t forcing function gives us a forced response c e to the minus 1t. We would plug that into our differential equation and find that c e to the minus t plus 3 times minus c e to the minus t plus 2c e to the minus t equals our input 2e to the minus t. Equating the two sides, we would see that all the terms in the left-hand side would actually sum to 0. And so we would have a 0 equals 2e to the minus t, a contradiction. And so there is no solution for this. There is no value of c that would work. And this is typically what would happen if we forget to check this special case and it's appropriate. Then when we carry forward our solution method, we'll see that it will lead to some kind of contradiction. So that's a tip-off that our assumption was wrong. And our wrong assumption was that the forced response had this form, c e to the minus 1t. In reality, we should have invoked this special case, which says my forced response, because we do match a term of the natural response, is not c e to the minus 1t, but c times t e to the minus 1t, because this term appears once in the natural response of the system. So we have a c times t to the first power times our exponential function. Then if we carried this forward, we would plug this assumption, ct e to the minus t, into our differential equation. And the second derivative then has many terms, as does the first derivative, because we now have two functions of time, so we have to apply a chain rule to the derivatives. So for example, the first derivative, we would take first the derivative of the first term, t, which is 1, times e to the minus t, the second function, and add the first function, ct, times the derivative of the second, which would be the minus 1 out in front, e to the minus 1t. So that's how we would get these terms. And similarly, if we differentiate the first derivative of yf of t, we would get the second derivative terms. We set that equal to x of t, the 2e to the minus t again, and collect up our terms. And we see that all of these different terms add up to, well, the ct e to the minus t terms. We have plus 1 here, we have minus 3 here, and plus 2 here. They cancel out, which is good because we don't have any t e to the minus t terms on this side. Fortunately, they cancel out, just leave me a 1 c e to the minus t equals 2e to the minus t, so c must be 2. So in this case, our forced response would be 2t e to the minus t u of t. And so that would be combined with a natural response to find the zero state response of the system, and the rest of the differential equation solution method would carry on as it would in the normal method. This is the only part that we would have to change in the whole method when we had this special case of the forcing function matching a term in the natural response. The second special case arises when the characteristic equation of the differential equation has repeated roots. For example, if we used our derivative operator to find the characteristic equation from the left-hand side of the differential equation, and it came out to be s squared plus 6s plus 9, and we were trying to find the roots of that, so we'd set it equal to 0. This is a perfect square, so we have two values of s, but they're both minus 3. When we have this condition where we have more than one root to the characteristic equation giving us the same term, then we have to change our assumption about what the form of the natural response is for the system. This is what moves us from our first row of the different options for the forms of the natural response, where we have a real root and it gives us a k e to the rt, to when we have a repeated real root, rp plus 1, where p plus 1 is the number of times that the root appears. So in our previous example, that root appeared twice, so p plus 1 would be 2, or p would be 1. What we get then is still our familiar e to the rt times a constant, but the second root would generate an e to the minus rt times another constant times a t term. So we would still get two natural response terms from our two repeated roots. One would be with just a constant, one would be a constant times t out in front. And so the assumption for the natural response of this system, whether we're solving for a zero state response or a zero input response, would be an unknown coefficient times e to the minus 3 and an unknown coefficient times t times e to the minus 3. And that would affect both how we solve for the zero input response and the zero state response. We would use these assumptions for both of those. The rest of the method, finding forced responses, combining responses, would be the same as in the normal technique. Now here's a perfect cubic. If this was our characteristic equation for a third order system, and we had three roots of s equals minus 3, then the natural response would be the form some k1 e to the minus 3t plus k2 t e to the minus 3t, and this third root would generate now a kt squared e to the minus 3t term. So each root of the characteristic equation has to give us a unique form in the natural response. And so we continue to raise the powers of t to accommodate each of the repeated roots. Now if we combine our special cases, if we had a case like this where we had multiple roots of the characteristic equation that were the same, giving us a new unique form of the natural response, and then what if this particular system we excited with an x of t that had the same shape too, e to the minus 3t, what happens then? Well, we still use this special case formula for the natural response due to the repeated roots, but the x of t then generates a forced response that is now a t cubed times e to the minus 3 with some unknown coefficient out in front. That's what that table of forced responses was telling us about how the power of t is related to how many times that same root appears in the characteristic equation. In this case, it appears 3 times, so we need a t cubed in front of our exponential term for the forced response so that it's different from all the other terms from the natural response. So let's take an example. Let's find the zero input response of this second order system. Y double prime of t plus 2y prime of t plus y of t equals x of t. Again, a single input case equation. And we're going to excite it with an input 5 e to the minus 2t u of t. And it has second order system, has two initial conditions, y of 0 equals minus 1, y prime of 0 equals 3. We extract the characteristic equation, which looks like an s squared plus 2s plus 1 equals 0. Factor it, we have a perfect square. S plus 1 quantity squared equals 0. So two repeated roots, s equals minus 1 and minus 1. Our zero input response then, which takes on the form of a natural response, has the form k1 e to the minus t from our first root and k2 t e to the minus t from the second root. The rest of the solution method goes on as before. So to find the unknown coefficients, we would find the zero input response at time t equals 0. So this is k e to the 0 plus k2 times 0 e to the 0. So we get k1 times 1 plus k2 times 0. Leaves us just the k1 equals our initial condition value for y of 0 equals minus 1. So we get a value for k1 right off the bat. Then we use the second initial condition. We have to take the derivative of our zero input response, which is minus 1 k1 plus k2 times e to the minus t minus k2 times t e to the minus t, breaking up this second derivative into two parts. And we're going to evaluate that at t equals 0 to go with our initial condition. So t equals 0, this becomes minus k1 e to the 0, which is 1, plus k2. And again, the k2t e to the minus t, when we set t equal to 0, this term goes away. So I only have these two terms, minus k1 plus k2 equals 3. Since I know k1 is minus 1, we can determine k2 must be 2. And so we can get the zero input response is minus 1 e to the minus t plus 2t e to the minus t for time t greater than 0. So again, all that changed in our whole process was the initial assumption we made about the shape of the natural response due to these repeated roots. The rest of the method carried on the same. If we were finding a zero state response, we would have found a forced response and added a natural response piece. The forced response due to this particular input would have had the form c e to the minus 2t, and the natural response terms would have been, again, some new coefficient k3 times e to the minus 3 plus k4t e to the minus t. And I would have solved for c using my conventional method for finding the forced response. It doesn't overlap with either of these roots, so we would find that normally, and we would use this assumption with 0 initial conditions to find the 0 state response. Now let's relate this to system stability with a few cautionary examples. Here's a third-order system. The third derivative of y plus 3 times the second derivative of y equals x of t. And so I need 3 initial conditions to solve this particular single input case, and we have those here. We find the characteristic equation of that. This would be an s cubed plus 3s squared equals 0. Factoring that out, we have 2 roots at 0 from this s squared term, and 1 root at s equals minus 3 from this third root. Our 0 input response then has the form of e to the 0 times k0 plus k1t e to the 0 from these first 2 roots plus k2 e to the minus 3 from this third root. And e to the 0 we know is 1, so this 0 input response is a constant plus another constant times t plus a constant times e to the minus 3t. This is again just following our methodology for handling repeated roots. And if we were to solve this for these particular initial conditions, we would find that the 0 input response from some leftover inputs that generated these initial conditions would be 2 times u of t plus 2t u of t plus 1 e to the minus 3t u of t. Now, what does that look like? If we plotted that response for t greater than 0, we have a unit step, we have a ramp. The unit step has a height of 2, the ramp has a slope of 2, and we have a decaying exponential, 1 times e to the minus 3t. If we put those together, it would look like this. Even though we have a decaying exponential, this ramp is increasing faster than the exponential is decreasing. So the 0 input response of the system, the response of the system to the initial conditions, without even applying any new input to it, is going off to infinity because of this 2t term. That doesn't look like a stable system to me. Now let's look at another cautionary solution. Here's a simple first-order system. Y prime of t plus 3y of t equals the second derivative of the input with respect to time. Only need 1 initial condition to solve this one, so we'll even start with a relaxed system, make it really simple, and say we're going to apply an input now that's 4 e to the minus 2t u of t. But let's check out the characteristic equation of the system. The first derivative of y gives us an s, the 3y of t term gives us a plus 3, so the characteristic equation of the system is s plus 3 equals 0, the root is s equals minus 3, which will give rise to a natural response term that's a k e to the minus 3t. That's different in form from our input signal, and so this is not the special case due to either having repeated roots or having a natural response form and a forced response form that are the same. Let's go ahead and solve the single input case first. First we demote the equation to y. First we find the single input case of the system, which would be working with a differential equation y prime of t plus 3y of t equals just x of t, not its derivatives. For that we want to find the forced response. The forced response for an input of the form e to the minus 2t is an unknown coefficient times e to the minus 2t. Its first derivative would be minus 2c e to the minus 2t. We plug those into the single input case differential equation, which would be y forced response first derivative plus 3 times the forced response equals the actual input x of t. So we have our minus 2c e to the minus 2t for the first derivative of the forced response, plus 3 times c e to the minus 2t equals the actual input 4 e to the minus 2t. The e to the minus 2t's cancel out everywhere. That gives us 1 times c equals 4, so c equals 4. Finding the 0 state response for the single input case of the system, we would take that known forced response, add an unknown natural response term, k1 e to the minus 3t, coming from this root of the characteristic equation. Use our one initial condition for a zero state response, that's the initial condition equal to 0. Plug in time t equals 0, we get 4 plus k equals 0. So k must be minus 4. So the two parts of our single input case zero state response are 4 e to the minus 2t, the forced response, minus 4 e to the minus 3t, the natural response piece. Now that's for the single input case equation. We want to find the zero state response for the general case. So for that, we need to do everything to our zero state response from single input case that happens to our x of t on the right hand side. And so the zero state response for the general equation is the second derivative of the zero state response from the single input case. And again, we'll be careful to include our u of t's in the single input case zero state response when we're going to be doing derivatives. If we take the first derivative of this function, it would be the derivative of the first function times the second function plus the first function times the derivative of the second. This first function has a derivative of minus 8 e to the minus 2t from this term, plus 12 e to the minus 3t from the second term, all times u of t, plus this whole term times the derivative of u of t, which is a delta of t. This term is multiplied by a delta of t, so we evaluate it at the time the impulse fires, which is at t equals 0. So we plug in t equals 0 to these exponentials. They all become e to the zeros, and we get 4 minus 4, or 0, so this whole term drops out. And our first derivative of the zero state response for the single input case is just our minus 8 e to the minus 2t plus 12 e to the minus 3t, all times u of t. Now we're not finished yet. We need to take another derivative to get the zero state response of our general case. So we'll take the time derivative of this expression and get the derivative of the first, 16 e to the minus 2t minus 36 e to the minus 3t times u of t, plus this whole term times a delta of t, the derivative of the unit step. Once again, we'll evaluate this time function that's multiplying a delta of t. We'll evaluate it at the time that the impulse fires, which is at t equals 0. We'll get a minus 8 e to the 0 plus 12 e to the 0, which is a positive 4. So this time we do have a delta function. And so this is the kind of case where it was necessary for us to include our unit steps in our zero state response in order to uncover the fact that we got a delta function here. Now, in addition to demonstrating the necessity of using those u of t's in case this happens, we've also got a very curious case here. I have a linear constant coefficient differential equation. It's a relaxed system. I'm putting a bounded input signal into my system. That input signal at 4 e to the minus 3t is a very well-behaved decaying signal. It's causal, so for t less than 0 it has a value of 0. At t equals 0 it jumps up to the 4 out in front. And after that it decays down exponentially towards 0. So this is definitely a bounded input. We can put a boundary on either side of this, and we have a completely bounded input. However, our output has two decaying exponential terms, which are causal, and those are fine, but it has this term. It has an impulse that for the instant at time t equals 0 is definitely not bounded. This is going to infinity. And so even though I put a bounded input signal into my system, I got an unbounded output. By our BIBO stability requirement, this would not be a stable system. And that's in fact correct. This is not a stable system, but I would have liked to have found that out before doing all this work. I would really like to be able to look at this differential equation and conclude right away, is this stable or not? That's the ability we'd like to develop now. So for stability, again, we began with this definition of bounded input, bounded output stability. Namely that if I put a bounded input signal into my system, and for every possible bounded input signal I could put into my system, I have to get out a bounded output signal. So if x of t is bounded, meaning if there's some finite value m, that its absolute value stays below for all time, then whatever y of t is, however it responds to that bounded input, that output signal also has to be bounded, possibly by a different value, maybe more, maybe less, but it has to be bounded. It just can't go off to infinity. In this case, where we had our two repeated roots at 0 and another real root at -3, and gave us this 2tu of t zero input response term, that even without putting an input in, was going off to infinity. So definitely not BIBO stable. In our second case, we had another bounded input, an exponential, that the response of the system was an unbounded delta function. Now, how do we tell whether or not a system is stable or not? Well, there's two criteria. First, every root of the characteristic equation has to have a negative real part in order for the system to be stable. That's just another way of saying your natural response has to be constrained in order for your system to be bounded. If you're going to have an exponential response, you want the real part to be negative, so it's a decaying exponential, not a rising exponential. So here, if this is the characteristic equation of our system, it has two real roots. They are both negative. This would be a stable system, because its natural response would be a k1 e to the -1t plus k2 e to the -4t. These are both decaying exponentials, so the natural response is stable. Here we have a different characteristic equation that has a negative root and a positive root. This would be an unstable system. It doesn't satisfy our criterion. All the roots of the characteristic equation have to have negative real parts. In this case, this +1 root of the characteristic equation would give us a k e to the +1t term in a natural response. This term is always going to want to push our response up off to infinity. Here's a characteristic equation that actually has a set of complex conjugate roots that are 1 plus or minus j omega. This would be an unstable system. The natural response, if we looked up this in our table, would be e to the real part of the root t times a cosine omega coming from the imaginary part of the root t, and perhaps plus some sine term. The problem here is this real part of the root gives us an e to the plus t, a rising exponential. So even though it's oscillating, that oscillation is getting larger and larger and larger. This would be an unstable system. Here's a very similar system that has a similar complex conjugate root, except the real part is negative in this case. My natural response now then is some k e to the -1t cosine. That's okay. It's okay that it's oscillating back and forth because it's got this exponential, this decaying exponential envelope, making the oscillation die out over time. That would be a stable system. We only look at the real part of the roots. If they're real or imaginary or complex, we look at the real part. If they're real roots, they have to be negative. If they're complex conjugate roots, the real part has to be negative. If they're purely imaginary, then I have no exponential and I have a cosine natural response. We have an oscillator, which would also be unstable. So would we have spotted this in our two examples of unstable systems? Well, the first one had two characteristic equation roots at 0. They were real, but they weren't negative. And 0 doesn't work either. For 0 roots, particularly with the repeated root, we got the t e to the ut term and it went off to infinity. So if we had looked at the characteristic equation of this particular system, we would have been able to tell right off the bat that this was an unstable system. The other problem we're looking for is we have to compare the highest degree of derivatives on the x side compared to the highest order derivative on the y side, the thing we call the order of the differential equation. For a stable system, the degree of the highest derivative of x cannot exceed the order of the differential equation, the highest order derivative of the y side, the left-hand side. So if we have a first order system, so we only have a first derivative of y, if I have a second order derivative or third derivative of x, that's an unstable system. The x derivative cannot be at a higher order than the y. It can be the same, it just can't be a higher order. If it is, then it's an unstable system. So way back in that problem, the one that generated the delta function, we had a first order system, but we had a second derivative term on the x side. Notice if it had only been a first derivative, we would have only taken one derivative of the zero state response from the single input case, and that was fine. It was in the second derivative that we generated this impulse function that made this system unstable. It had an unbounded output for a bounded input. So I could have evaluated this differential equation right at the very beginning before doing all this work and seen, oh, we have a higher order derivative of x than y. This is going to be an unstable system. So here's a couple practice examples. Here's a differential equation for a system. First we compare the derivatives. On the y side I have a second derivative. On the x side I have no derivative, so that's okay. We find the characteristic equation. It's s squared minus 3s plus 2 that has roots of s equals plus 1 and s equals plus 2, because factoring this would give us an s minus 2 times s minus 1. These roots are real, but they're both positive, so this would be an unstable system. Here's a similar one where we change the minus sign to plus sign. Again, we have no derivatives of x, and we have a second order derivative of y, so it's that part of the stability requirement is okay. If we factor this characteristic equation, s squared plus 3s plus 2 equals 0, the factors are s plus 1 times s plus 2, so the roots are minus 1, minus 2. Both are real and both are negative, so this is a stable system. Here's a first order system with a characteristic equation s plus 3 equals 0, so it has one real root. That's okay. But we have a second derivative of x on one side, a first derivative of y on the other side. So like in our example, this would not be a stable system due to this higher order derivative of x than we have of y. And so with that, we'll pause at this point and let you tackle some of the homework problems with the special cases for solving differential equations for our two special cases of the forcing function being the same form as one of the terms of the natural response, or the natural response having repeated roots. And you can also proceed on to look at being able to look at differential equations describing systems and determine whether or not they'll be stable or not based on their roots of the characteristic equation and the orders of the derivatives in the term.